turn on my presentation. Yeah, so let me start by saying what we will not cover today. We will focus on the fundamentals of doing supervised land cover classification in Google Earth Engine. But what we will not do is get into the different types of classification algorithms that are there or their characteristics. We will not look at sampling design and how to collect data, training data, to label data, and all of those kinds of aspects. We won't get into too much depth on that. And we also won't look into the ideas of uncertainty in both the inputs and the outputs that go into supervised land cover classification. So I will start with an example image of Bangalore city from the Copernicus Sentinel-2 satellite. We start by seeing just the data from one band, which is the blue band from this image. It's not easy to make sense of this image. Being entirely in grayscale, we have to rely to some extent on the intensity of gray and to some extent on the texture of the image to recognize features in it. Still, we are able to recognize and distinguish built-up areas, which are light, from the areas that possibly have vegetation or water, which appear dark. But then in the next frame, as I add red and green bands and display a true color image with three bands, red, green, and blue, more features become discernible. And yet it continues to be hard, for example, to differentiate vegetation from water, or for instance, roads from built-up areas. But then, once I replace the RGB bands with the red, near-infrared, and shortwave infrared bands, features that were previously ambiguous, like vegetation and lakes, or features that were previously indiscernible, like roads, now become clear and prominent. So there are many things going on here, but I want to focus on two. First, when we look at each image as humans, we are always unconsciously trying to recognize patterns. We recognize patterns in hue, in the saturation, in brightness, texture, that we then associate with real world features like a lake, or a road. This is a perceptual rather than a computational task, and humans are generally very good at it. So, this is the way humans process large amounts of data, by breaking them into meaningful categories, or in other words, via classification. Second, as we have seen with just the blue band, the task of perceiving these real world features is very hard with very little data, but it becomes easier when we add both variety and quantum of data, as we did when we added information from the green, blue, near infrared, and shortwave infrared bands. The task becomes more and more possible. But then this is not without limits. As the complexity of the tasks grow, when we add more and more input data to the classification tasks, or as our tasks become more detailed and nuanced with respect to their outputs, we quickly begin to hit limits of human ability. But computers, as we know, are very good at handling such large and complex computational tasks, but they need help from humans, it turns out, with perceptual tasks. So wouldn't it be great if we could train a computer with this perceptual task, which it could then scale as the volume and complexity of the inputs and outputs grows? This is basically the problem that supervised classification solves. It's one of the powerful and generic machine learning approaches used to teach computers how to accomplish perceptual tasks that involve large input data and involve and also have subtly differing outputs, such as in assigning pixels in an image to meaningful categories. So, how is this done? Before we move ahead, it's useful to quickly remind ourselves about some remote sensing fundamentals. Differing land cover categories like water, vegetation, or built up areas all have very different spectral reflectance patterns. What do I mean by that? In other words, they absorb and reflect very different kinds of light in the visible and non-visible parts of the spectrum. We can use these differing combinations of reflectance values to create what are called spectral signatures for different land cover types. Think of a signature like the shape of a graph for each of the land cover classes. As we can see, the shape of the graph we have for water here is of this sort. And for vegetation, it has a pattern that's very different from, say, built up areas. And what I want to highlight is that if you just look at the blue, as we saw, it was not very easy for us to distinguish between vegetation and water using just the blue band, whereas we did see that the built up areas were very different. But then, the moment we put in near infrared, the the reflectance patterns of built-up areas and vegetation become more similar, but they become very different from the reflectance patterns of water. And on the other hand, if we add software, the shortwave infrared, we start to see that all of them, built-up areas, vegetation, and water, have very different reflectance patterns. Now, we can use all of this to try and help us. So now out of this, we are able to generate a signature for a built up areas, vegetation, and water. And we can try and, if we get a pixel with an unknown kind of we can match it up to unknown signature. We can match it up to one of these and see which of these it's closest at fitting. So before, so now how do we do this? Uh, First, what I will do is I will run through the various steps involved in supervised classification of land cover types in the presentation itself. And then we'll move to Earth Engine, where we will actually run each of these steps in a simple and then a more complex example each of supervised classification. What I want to start by saying is that the entire code that we are going to be working off is available on this at this link. So you can go back to this. This is a permanent link, and you'll be able to access the code as we have seen here. And so even the graph that was published earlier and so on, you'll see links to many of these that you can access as we go forward. So there are 6 steps that I have kind of summarized that are necessary for us to get moving with supervised classification. So first is to prepare relevant image data. So what we will first do is get identify a sensor, a satellite image, a satellite sensor from which we will get images, and we will import that into a collection. And then we want to look at this image collection with reference to a certain point or region, which we will then select. And then once we have done that, use appropriate spatial, temporal, and other kinds of filters, some of which Ujjwal spoke to you about last time, and they're available. If you're not sure what this is, you should go to the docs and see. These are really, really powerful tools that Earth Engine offers you to try and start with vast amounts of data and very quickly narrow down to the things that are of interest and relevance to you. So we use spatial, temporal, and metadata filters to obtain a subset of images that we then composite into a single image. So we will do that using a median composite here, and then we will display that image. And after that, we will get down to label data. I will show you very quickly how we can label data and put label data together in order to start our classification exercise. Alternatively, if you have collected data in the field, or if you're going to do this on your own using the image that you have just, the composite that you have just displayed, you are able to do that either importing an Earth Engine asset or from a shapefile, and there are ways in which you can do that, to which I have put a link as well. And then what we do is we take these labeled data points and then create a signature for each of the classes that it represents using the composite image. So as we saw with the graphs that I showed you about the built up vegetation and water areas on your screens a moment ago, we will create signatures for the different land cover types. And using those signatures, we will try and create a classifier, a random forest classifier is what we will use. And we will try and create a classifier which we can then use on the image to classify pixels that are unknown, that have not been known, and to tell us which of the categories it belongs to. And the way the classifier works is quite simple. And you can actually replace the random forest classifier with, say, a cart, a classification or a regression tree classifier, or a support vector machine classifier. And that's quite simple to do in Earth Engine, and that's exceedingly powerful. And then we apply the classifier and generate a classified image. We will see how to do that. And then finally, this is of no value if we do not know how good we have been at classifying something that is actually a real world category. So we will try to find out how accurate we have been with our classifier. So these are the steps that we will be looking at when we get to our, okay. Example, I'd like to begin with this example. So as I said, the same steps that I mentioned to you, I have outlined here. So if we did, so what I'm going to do to begin with is to run just the the first parts of our script where we load images from the Copernicus, the Sentinel-2 satellite, and we pick an area which is from the Valparai Plateau in Tamil Nadu in southern India. You'll see in a moment why that's the place of interest we've chosen. And we will filter it based on location, based on dates, based on metadata, and then create a median composite and select just the bands that carry information on each of these pixels, rescale their values, and then create one composite that we will then display. So, and that's what we will be doing right now. And as you can see, so what the area that we are seeing right now is an area which has some vegetation. It looks like it's the backwaters of a dam, and there are some drawdown areas of bare earth and so on that we can see in this image. So now what I want to show you is that as I start opening up, yeah, so we can add features as I have already done here. What I have done is I have put a set of points to denote which is water and which is vegetation. Now I could start by trying to get signatures of water and vegetation from this. But since I also want to show you how you can actually add your own features, what I will do is also show you how to create a new feature collection. So let's say I wanted also to segregate not just vegetation and water, but bare earth around the dam. What I can do here is that I can click on a new layer, and I can go to this wheel here and choose feature collection, and I will call this bare soil. And what I will do is I will add a property to this feature collection called label, which is just an index number of the uh, okay. Uh, so now I can go about adding points that represent areas that are bare soil, because that is the third kind of uh, class that I want to be able to classify using this. So I have added, as you can see here, 10 points of each of these. And now what I will do is I can actually merge all of this data together as so I have training points from water, from vegetation, and from bare soil, and I can merge this. So since after all of these have been merged, we can get the signatures of the land cover types that we have chosen here, and train a classifier based on the property that we've called label, which has, so they have an index number of 0, 1, and 2, which is the label, and that's what one needs to use to train a classifier here. And after that, we can produce a classified image, which we can then display using certain colors on this palette. And we will see how we can do that. So now if we run this, we should be able to see one layer, which is the composite that is loaded. But in addition, as you can see, now from having started just with vegetation and water, we now have three classes of land cover that we have managed to classify, which is water, bare soil, and but how good has this been? So in order to do that, there are built-in tools that allow you to assess the accuracy of what you're trying to do. And there is something called a confusion matrix that tries to say how much of the label data you got right. But this is what we are getting here is just the training accuracy, which is a measure of how well the classifier classifies data that it has already seen. And this is not really very useful. But when you have a larger data set, as we will see in a moment, you can keep one fraction as training fraction and train a classifier, and then use an independent validation fraction to do a much more reliable test of the accuracy of your classifier in labeling data that it has not previously seen. So now we'll run this and try to see what the outputs are with. So it has, so all the training data points that we have used have been, when the classification happens in the classified image, they end up in the right categories. So we get a training accuracy of 1, which is 100%, which is not very useful or surprising at this stage. But now let's get to a real world example. And in the real world example, what I will do is point to certain key differences from the simple example that we began with. So we will begin, the points I want to mention are that we will be merging very different kinds of image data from different kinds of sensors, from bands within different bands within the same sensor. We will be seeing how to import a large labeled set of data from assets. We will also see how to create a training and validation fraction from the labeled data, and see how to do an accuracy assessment. So without further ado, let's go to this, which actually also happens to be a starting script, a starter script for you to undertake this times the Earth Engine challenge that Google has kindly put together. So we will not look at some of the early parts of this, which is meant for visualization. So I will focus on parts of that script that has already been shared with you on that call, and I want to call your attention to specific parts of this. So here what we have done is right at the top, we have an import, which is from an Earth Engine asset that we have imported this table called VLP underscore table, which has our labeled data. So what we now do is we take this labeled data set, add a random column, which adds to every row a random number between 0 and 1. And so we use 75% of the data to train and another 25% of the data to validate what classification, the classifier we've got, and see how accurate it is. So the way we do this is that we pick rows that have a value less than 75, and then pick rows that have values of greater than 75, and then get a fraction uh, for training and validation. So that's one part that I wanted to focus your attention on. The second thing I wanted to do is that you are not stuck with just having to take one set of images and create a median. Now, you could, for instance, be adding NDVI or the NDWI if you're interested in water. And then you can add these as bands to your composite, improve your classifier. And that is largely the task we are hoping you'll be able to do this time with your own creativity and ingenuity. You can also add other kinds of sensors, like this is the ELOS elevation data set, from which you can bring the elevation data, and you can add all of these bands to your composite such that you have now a composite that contains not just the raw band data, but also the band arithmetic in terms of NDVI and so on, and also elevation data uh, from ALOS and so on. So now with that composite, you're now doing a training, you're getting signatures from just the training fraction of your data set and training a classifier here. And based on that, you create a classified image. Now you go back to your validation fraction and get the signatures of data points in your validation fraction, and then create a confusion matrix where you see how well the labels that you actually had on your validation data points match up to the labels that they get once they are classified using your classifier. And this is a measure of the accuracy of your classification. And what we have managed to get so far is we have, I think, about 8 categories here. uh, yeah, we have 8 categories. They're not continuous numbers, and this tells you, the confusion matrix tells you how many of the how many of the points in each of these categories have been classified correctly. In which case, most of the points would lie along the diagonal here. Off diagonal elements generally signify how, I mean, the places where your classifier is not performing as accurately as it would. So where we are right now is that we have trained a classifier with a model that has an accuracy of 81.3%. And what we would like to do, and at this point I invite Ujjwal to add anything more he has to this, we would like you to improve the accuracy of this classifier so that you leverage on what we have tried to learn today about supervised classification and solve a real world problem in terms of improving the classification accuracy of a land cover for this area of Valparai in Tamil Nadu, which has a very interesting mix of landscape types that you will read about a little bit more in the example. So at this point, I hand over to Ujjwal for any comments.